Suppose f has a power series representation f of x equal to the sum n equals 0 to infinity a sub n times x minus c raised to the n. If we were to expand this series, it would look like this. F of x equal to the first term, a sub 0, plus the second term, a sub 1, times x minus c, plus a sub 2 times x minus c squared, plus a sub 3 times x minus c cubed, plus, and then this would continue until we got to the nth term, which would be a sub n times x minus c raised to the n, and then it would continue infinitely. So let's imagine what the first derivative would look like. So the first derivative of this expansion of this series would start with the elimination of the first term. That would be constant, and its derivative would be 0. The derivative of the second term would be the constant a sub 1 times the derivative of x minus c, which would just be 1. And then continuing this process, we would have 2 times a sub 2 times x minus c raised to the power of 1 plus 3 times a sub 3 times x minus c squared plus, and then this process would continue. We finally would get down to the nth term, a n times a sub n times x minus c raised to the n minus 1, and then that would continue infinitely. Let's look at the second derivative. The second derivative now would find the first term, a sub 1, going to 0, and we would then have 2 a sub 2 plus, and then we would have 3 times 2 times a sub 3 times x minus c plus, and then this would continue until we got down to the nth term. We'd have n times n minus 1 times a sub n times x minus c raised to the n minus 2 plus, and then that would continue infinitely. Let's just do one more and see if we can see a pattern. So the third derivative, then, 2a sub 2 would go to 0. We would have 3 times 2 times a sub 3 plus, and then this would continue until we got to the nth, n times n minus 1 times n minus 2 times a sub n times x minus c raised to the n minus 3 plus, and then that would continue. Now I think we can come up with a pattern for the nth derivative at this point. So the nth derivative then of this function, or in other words, the nth derivative of the expansion of this series, would be n times n minus 1 times n minus 2, and this would continue all the way down to 3 times 2 times 1 times a sub n times x minus c raised to the n minus n. plus, and then that would continue. But what we realize is what that really is, the nth derivative then, would be n factorial times a sub n plus whatever follows, because n minus n is 0, so x minus c would be raised to the 0 power and just become 1. Now, if we consider this, following terms after this first one would have the form where they have some coefficient times x minus c raised to some exponent, and then continue on. But each term would have this form. Now, if we were to find the nth derivative at c, then each of those terms after the first would go to 0. X minus c, if x was equal to c, would be c minus c, or 0. So, the nth derivative at c would be n factorial times a sub n. Okay, so now let's solve for the coefficient, a sub n. We can do that by dividing both sides by n factorial. So a sub n would be the nth derivative of the function f evaluated at c divided by n factorial. So a sub n equal to the nth derivative at c divided by n factorial. Let's think about this a bit. We defined our function f of x as the power series n equals 0 to infinity a sub n x minus c raised to the n. So f of x would then have the form sum n equals 0 to infinity nth derivative of the function f evaluated at c divided by n factorial times x minus c raised to the nth power. This is what's known as the Taylor series. When c is equal to 0, we would have the form f of x equal to sum n equal to 0 to infinity nth derivative at 0 divided by n factorial times x raised to the n. And this is known as the Maclaurine series. So the Taylor series then is defined for any value of c. The Maclaurine series is defined when c has the specific value 0. So let's find the Taylor series that represents the function f of x equal to e to the x at the point c equal to 0. What that means then is, in other words, find the Maclaurin series for f of x equal to e to the x. Okay, well, let's consider some things. First, we might want to know, okay, well, what does the Maclaurin series look like? So let's notice some things about this. First thing we might notice is that n factorial never changes. So in any function that we're looking for a Maclaurin series for, this n factorial is never going to change. Something else that we'll note is that x minus c to the n is never going to change. For any Taylor series, and specifically for the Maclaurin series, that will just be x to the n, since c will be equal to 0. So what do? We must find a pattern that represents the nth derivative of f. So find a pattern that represents the nth derivative of the function f. So we'll just begin by finding several derivatives of the function f. F of x is equal to e to the x. Okay, well, this is not too bad for e to the x because the first derivative is e to the x. The second derivative is e to the x. And this, of course, is going to continue forever. So the nth derivative is e to the x. So the nth derivative at c would be e to the c. But we're finding a Maclaurin series, so we would have the specific value of c to be 0. So the nth derivative at 0 would be e to the 0, or 1. So now, filling in what we know, we would have f of x equal to sum n equals 0 to infinity. The nth derivative at 0 is 1 over n factorial times x to the n. So here is our Maclaurin series representation for the function f of x equals e to the x. So let's find the Taylor series for f of x equals the natural log of x at c equals 1. Here is our Taylor series representation for a function f. And again, we need to find derivatives of the function f. The first derivative would be 1 over x. Now, I might represent that as x to the minus 1. The second derivative would be minus 1 times x to the negative 2 power. The third derivative would be 2 times 1 times x to the negative 3 power. I might do this a few more times until I see a pattern coming up. The next one would be negative 3 times 2 times 1 times x to the negative fourth power. The fifth derivative would be 4 times 3 times 2 times 1 times x to the negative fifth power. And now I think I might see a way that I could write the nth derivative according to this pattern. It's alternating, so I would have negative 1 raised to a power, and that power would need to be oriented so that the first derivative would be positive, the second derivative would be negative, the third derivative positive. So odd derivatives would be positive and even derivatives would be negative. Then we notice that we have n minus 1 factorial and then x raised to the negative n. So we could write this as negative 1 raised to the n minus 1 times n minus 1 factorial divided by x to the nth power. So to find the Taylor series, we would need to find the nth derivative at c. The nth derivative at c would be negative 1 raised to the n minus 1 times n minus 1 factorial divided by c raised to the nth power. But we're finding the Taylor representation when c is equal to 1. So the nth derivative when c is equal to 1 would be negative 1 raised to the n minus 1 power times n minus 1 factorial. Now we can write our Taylor series representation, f of x equal to the sum, n equals 0 to infinity. The nth derivative at c is negative 1 raised to the n minus 1 times n minus 1 factorial. This will then be divided by n factorial and then multiplied by x minus 1 to the nth power. Now we could write this a little bit more simply, actually, because we remember that n factorial could be written as n times n minus 1 factorial. So we would have the sum, n equals 0 to infinity, negative 1 raised to the n minus 1 times n minus 1 factorial over n times n minus 1 factorial times x minus 1 raised to the nth power. Now these n minus 1 factorial factors will cancel. And what we're left with then is f of x equal to the sum n equals 1 to infinity, negative 1 raised to the n minus 1 times x minus 1 raised to the n divided by n. So now the question becomes, for what values of x is this series convergent? In order to find out, we might use the ratio test. So we would find the limit as n goes to infinity of the absolute value of minus 1 raised to the n plus 1 minus 1 times x minus 1 raised to the n plus 1 over n plus 1 divided by minus 1 raised to the n minus 1 times x minus 1 raised to the n over n, which we could invert and multiply and wind up with the limit as n goes to infinity of the absolute value of, now we would have negative 1 raised to the n times x minus 1 raised to the n plus 1 over n plus 1 times n over negative 1 raised to the n minus 1 times x minus 1 raised to the n. This would give us then the limit as n goes to infinity, the absolute value of negative 1 raised to the n times n times x minus 1 times x minus 1 raised to the n over negative 1 raised to the n minus 1 times n plus 1 times x minus 1 raised to the n. And now the x minus 1 raised to the n factors would cancel. And we might consider that negative 1 to the n, negative 1 raised to the n minus 1 are always going to be opposites, which would give us a negative factor, but in absolute value would always be positive. N and n plus 1 are always going to be positive, so they can come out of the absolute value. So we have the limit as n goes to infinity of n over n plus 1 times the absolute value of x minus 1. Now we could write the limit as n goes to infinity of, and dividing every term in this first fraction by n, we would have n over n over n over n plus 1 over n times the absolute value of x minus 1, which would give us the limit as n goes to infinity of 1 over 1 plus 1 over n times the absolute value of x minus 1. And the limit as n goes to infinity of 1 over n is 0. So this first factor then would just be 1. And the whole thing then is just equal to the absolute value of x minus 1. Now, in order for this to be convergent, we would need for this value to be less than 1. Which means then that x minus 1 has to be between negative 1 and 1. Which means then that x would have to be between 0 and 2. So now we need to check the endpoints. Now, if we substitute x equal to 0, we would have the sum n equals 1 to infinity, negative 1 raised to the n minus 1 times 0 minus 1 raised to the n over n, which would give us the sum n equals 1 to infinity negative 1 raised to the n minus 1 times negative 1 raised to the n over n. Now these two factors, negative 1 raised to the n minus 1 and negative 1 raised to the n, would always be opposites. So their product would always be negative 1. So we have the sum n equals 1 to infinity negative 1 over n, which we could write as the opposite of the sum n equals 1 to infinity 1 over n, which we know is divergent. This is the divergent harmonic series. So now we can substitute x equal to 2. So we would have the sum n equals 1 to infinity negative 1 raised to the n minus 1 times 2 minus 1 raised to the n divided by n. 2 minus 1 is 1 raised to the nth power, would always be 1. So this is just equal to the sum n equals 1 to infinity negative 1 raised to the n minus 1 over n. But this is the convergent alternating harmonic series. So what we have found is that the Taylor series representation for the natural log of x centered at c equals 1 would be sum n equals 1 to infinity negative 1 raised to the n minus 1 times x minus 1 raised to the n over n, and converges on the interval 0 to 2, not including 0 and including 2. So let's find the Maclaurine series representation, in other words, a Taylor series with c equal to 0, for the function f of x equal to the sine of x. So what we need to do is recall what the Maclaurine series looks like. It's the sum n equals 0 to infinity, the nth derivative of the function f evaluated at 0 times x to the n divided by n factorial. So we begin by looking at the function f of x equal to sine x and then find derivatives looking for a pattern. The first derivative would be the cosine of x. The second derivative would be the opposite of the sine of x. The third derivative would be the opposite of the cosine of x. The fourth derivative would be the sine of x. And we see that there's a bit of a pattern, but the problem comes in that it isn't alternating. The nth derivative then would be a sine or a cosine, but then would be either positive or negative. The 0th derivative, or in other words, the function itself evaluated at 0 would be 0. The first derivative evaluated at 0 would be 1. The second derivative evaluated at 0 would be 0. The third derivative evaluated at 0 would be negative 1. The fourth derivative evaluated at 0 would be 0. And again, we have a little bit of a problem here in that the nth derivative doesn't really get itself a pattern going other than it's 0 and then 1 and then 0 and then negative 1 and then 0 and then 1 and 0 and negative 1. So it becomes difficult to express it in terms of n. So we don't really get a pattern in terms of n. So what we might do then is look at, well, what does the Maclaurine series itself look like in all of these terms? So this Maclaurine series then, sum n equals 0 to infinity, nth derivative at 0 times x raised to the n over n factorial. Let's see. This would have the form f of 0 plus f prime 0 times x plus f double prime 0 x squared over 2 factorial plus third derivative at 0 x cubed over 3 factorial plus fourth derivative at 0 x to the fourth over 4 factorial plus, and then on into infinity. So what would these terms then look like? Well, the first one would be 0. We decided that f of 0 was 0. The second one would be f prime of 0 was 1, so it would just be x. The third one would be 0. The fourth one would be negative 1 times x cubed over 3 factorial. Then we would have another 0. Then x to the fifth over 5 factorial, and then another 0. And then negative 1 times x to the 7th over 7 factorial. And now we start to see a pattern. This actually becomes x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... Now I think we can define a series here, but here's the problem. We said earlier that no pattern arises in terms of n. And if we were to try to define this pattern, it wouldn't be in terms of n. We'd have to define another variable. Like we might, for instance, use k instead of n. So we might write this then as the sum k equals 0 to infinity, negative 1 raised to the k times x raised to the 2k plus 1 over 2k plus 1 factorial. So the next question then becomes, well, when is this thing convergent? So we could do the ratio test and find the limit as k goes to infinity of the absolute value of -1 raised to the k plus 1 times x raised to the 2 times k plus 1 over 2 times k plus 1 factorial over -1 raised to the k times x raised to the 2k plus 1 over 2k plus 1 factorial. And doing some algebra and inverting and multiplying, we'd have -1 times -1 raised to the k times x raised to the 2k plus 3. Distributing the 2, we have 2k plus 2 plus 1. And then in the denominator, we again have 2k plus 3 factorial. And then inverting and multiplying, we have 2k plus 1 factorial over -1 raised to the k times x raised to the 2k plus 1. Now, so far, we can see that the -1 to the k's will cancel, and in absolute value, the -1 will have no effect since it will always be positive. So we can just write this as the limit as k goes to infinity of the absolute value of, we could write x to the 2k plus 3 as x squared times x raised to the 2k plus 1. We could write 2k plus 3 factorial as 2k plus 3 times 2k plus 2 times 2k plus 1 factorial. Then we would have 2k plus 1 factorial over x raised to the 2k plus 1. And again, we have factors that cancel. The 2k plus 1 factorial will cancel, and the x to the 2k plus 1 will cancel. And we're left with the limit as k goes to infinity, the absolute value of 1 over 2k plus 3 times 2k plus 2 times the absolute value of x squared. But x squared is always going to be positive, so I don't need the absolute values anymore. Now, one thing that I do know is that the limit as k goes to infinity of 1 over 2k plus 3 times 2k plus 2 is equal to 0. So this whole thing is equal to 0, which is always less than 1. So this means then that according to the ratio test, this series converges for all x. So in other words, the interval of convergence is minus infinity to infinity. So let's talk about what this series then. So let's talk about what this series representation would look like. We were finding the series representation for the sine of x, and the series was a Maclaurine series. So what we have found is that this would be equal to the sum. Now, we changed to a k in order to accommodate for the fact that we were eliminating every other term when we were using n to represent the position of the derivative or the position of the term in the series. But k is just a letter just like n, so it doesn't matter if I use a k or an n. I can still write this as the sum n equals 0 to infinity, negative 1 raised to the n, x raised to the 2n plus 1 over 2n plus 1 factorial, and converges on the interval negative infinity to infinity. Now let's do the same for the cosine of x. F of x equal to the cosine of x. Now something that we might notice though is that the derivative with respect to x of the sine of x is the cosine of x. And those terms that we found when we found the Maclaurin series representation for the sine were x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, and then on out to infinity. So the derivative of the sine of x would then be the derivative of this series of terms. But this derivative would be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus, and then on out to infinity. So we can then similarly find a representation, sum n equals 0 to infinity minus 1 raised to the n, x raised to the 2n over 2n factorial on the interval minus infinity to infinity. So this would be the Maclaurin series representation for the cosine of x.